All right, so we're ready for section 9.3, simplifying radical expressions. So the very first thing, the very first concept we want to look at is what's called the multiplication property of radicals, right? So the multiplication property of radicals says the following. Let A and B represent real numbers such that the nth root of A and the nth root of B are both real, right? Then the following is true. The nth root of A times B is equal to the nth root of A times the nth root of B. Right, so notice if I have the nth root of a product, I can split that apart into two factors, right? So the nth root of A times nth root of B, right? You might wonder, well, how is that true? So I can actually show this using rational exponents and exponent rules. So the nth root of AB would be the same thing as A times B all to the power of 1 divided by n, right? But then when I have if my base is two factors, right? Remember the exponent rule, you're going to apply the exponent to each factor, right? So then now using the definition of rational exponents again, this would be the nth root of A times the nth root of B, right? Which is exactly what we were looking for, right? So just a quick example. Right? So like if I have the square root of 144, right, that's equal to the square root of 16 times 9, right, because 16 times 9 is equal to 144, so I could split those apart to be radical 16 times radical 9, and then, of course, I could actually find each of these, right, because these are both perfect squares. That would be 4 times 3, which is 12, right, which the square root of 144 we know is 12 also, right, but really we're just doing like this part just to practice applying that multiplication property of radicals, right? So another example of this is we can go the other way, right? So in other words, if I have the square root of 3 times the square root of 12, that's equal to the square root of 3 times 12, which equals radical 36, right? So it's important to note that we can go in both directions, right? So I can start with some product and split it up into factors and then split it up into two different radicals. Or if I have two radicals being multiplied with the same index, I can combine that as the product, the same root and the product of that, right? So this rule goes both directions, right? We can go both ways. So then concept 2 is titled Simplifying Radicals by Using the Multiplication Property of Radicals. So it's important to note the simplified form of a radical, right, which is this here. So we're just told consider any radical expression where the radicand is written as a product of prime factors, right? And just remember the radicand is what's underneath, right? So like if I have like the square root of 5, 5 is the radicand. Right, the radicand is the expression underneath the radical. So the expression is in simplified form if all of the following conditions are met, right? So the first condition is that the radicand has no factor raised to a power greater than or equal to the index, right? So remember, like if I put a 3 out here, that is referred to as the index, right? So that's the cubed root of 5. That 3 out there is the index, right? So then number 2 is the radicand does not contain a fraction. And the third condition is that there are no radicals in the denominator of a fraction, right? So I want to look at just some examples of this briefly, just to help this make sense, right? So if I have like the cubed root of x to the fifth, then this fails condition 1. Right? Condition 1 says that there's no factor raised to a power greater than or equal to the index, right? Well, there's the index, and 5 is a bigger power, right? So that fails that condition. Another one is if I have like the square root of 1/4, right? Because the second condition is that the radicand can't contain a fraction. Well, in this case, the radicand is a fraction, right? So this fails condition 2, right? So in other words, these are not simplified. And then if I have 1 divided by the cubed root of 8, this fails condition 3. Right? Because condition 3 is that there's no radicals in the denominator of a fraction. Right? Right, so then just another note is that if you have like the square root of x squared, the square root of x to the fourth, the square root of x to the sixth, the square root of x to the eighth, right, these all fail condition 1. And each of these can actually be reduced, right? The square root of x squared is just equal to x. The square root of x to the fourth is x squared. The square root of x to the sixth is x cubed, and this is x to the fourth, right? So those are all perfect squares, right? All right, so now we're ready to look at some examples of this. Example 1 is simplify the expression assuming that a is greater than or equal to 0, right? So we have the square root of a to the 11th, and I want to simplify this, right? And I know this is not simplified because the a is raised to a power bigger than the index, and the index here is 2, right? Remember, but we just don't write that with square root. So what we want to do is be able to simplify this. So I know that basically what I'm trying to find is, since the index is 2, I want to think about what's the biggest number that is a multiple of 2 that's less than 11, right? So in other words, it'd be 10, right? So a to the 11th, I could rewrite that as a to the 10th times a to the first power, right? Or in other words, just a to the 10th times a, right? And the reason why I'm thinking about getting that to be the biggest multiple of 2 that I can is because that's going to be how it'll reduce down, right? Using these radical multiplication radical properties. So the square root of a to the 11th would be equal to the square root of a to the 10th times a, right? So I just substituted that in for a to the 11th, and then I can apply the multiplication property of radicals that we just looked at. So this would be the square root of a to the 10th times a, right? Which this would be equal to, so I could rewrite a to the 10th as a to the 5 times 2, which is the same thing as a to the 5th quantity squared, right? So then this would be equal to the square root of a to the 5th quantity squared times, this would be square root of a, times square root of a, right? So a to the 5th squared, and take the square root of that, the square root's going to get rid of the square, right? So this becomes a to the 5th times the square root of a, right? And that's as simplified as we can get, right? So the second example, right? So again, I'm focusing on what the index is. The index is 4. So I want to think about what's the biggest number that's a multiple of 4 but less than 25, right? Well, that would be 24, right, in this case, because 6 times 4 equals 24, right? So what I'm thinking in my head is that, v to the 25th equals v to the 24th times v, and I can rewrite v to the 24th as v to the 6th all raised to the 4th power, right? Because 6 times 4 is 24. So when I'm working through this, right, I'd have the fourth root of v to the 25th equals the fourth root of v to the 24th times v. And then I can split these up, right? So this would be the fourth root of v to the 24th times the fourth root of v. And then I can rewrite v to the 24th as v to the 6th all raised to the 4th power times the fourth root of v. So since this part is to the 4th power, you're taking the 4th root, those cancel each other out. So this becomes v to the 6th, right, times the 4th root of v. Right? So that is simplified. Right? So in part B, same idea. This time we have two variables raised to exponents in here. Right? So again, what I'm kind of focusing on is this is an index 3. So I want to think of what's the biggest number that's a multiple of 3, but is less than 17. Well, I would say that's 15, right? So in other words, p to the 17th equals p to the 15th times p squared. Right, is what I'm thinking with that. And then here, the biggest multiple of 3 that's less than 10 would be 9, right? So that would be q, we could say q to the 10th equals q to the 9th times q, because I need one more q. Right, so then, it's kind of what my, thought bubble that's going on in my head when I'm looking at this, right? So then the cubed root of p to the 17th times q to the 10th is equal to, and I can split these up first. So that'd be a cubic root of p to the 17th times the cubic root of q to the 10th. And then now I can use my thought bubble beforehand to rewrite this. So I could rewrite p to the 17th as p to the 15th times p squared. And then I can rewrite q to the 10th as q to the 9th times q. Right? And then I can apply that multiplication property of radicals again to each of these. So that would be the cubed root of p to the 15th times the cubed root of p squared times the cubed root of q to the 9th times the cubed root of q. Right? So p to the 15th, right, that's the same thing as p to the 5th raised to the 3rd power, right? Because 5 times 3 is 15. Remember, power to a power, the multiplication, as you multiply for the exponent rule, right? So this would be times the cubed root of p squared times, and then this would be the cubed root of q to the 3rd all raised to the 3rd, right? Because 3 times 3 is 9. And then we'd have times the cubed root of q. So then now what I can do is, like, this guy is going to reduce down just to be p to the 5th, right? Because I have p to the 5th cubed and the cubed root of that, so these 3's essentially just cancel out, right? So this would be times the cubic root of p squared times, and then this guy is just going to simplify down to be q to the 3rd power, and then we have times the cubic root of q, right? So I can put these guys out in front, p to the 5th, q to the 3rd, and then I can apply the multiplication property of radicals just in reverse, if you will. When I multiply these two things together, where I put the arrows, that's just the cubic root of the product, p squared times q. Right, so this would be the cubic root of p squared times q. And that that's our simplified version of that expression. Okay. So then example 3, we have simplifying the square root of 24, right? So same ideas apply. So the first thing I would do with this is take 24 and find the prime factorization, right? So do a factor tree. So this would be 6 times 4 is a product of 2 factors of 24. And then let's keep breaking these up until we get all prime factors. So 6 is 3 times 2, and 4 is 2 times 2, right? So in other words, 24 is equal to 2 cubed, right? I have 3 factors of 2 times 3, right? So, so the square root of 24 is equal to the square root of 2 cubed times 3, right? So this is not simplified. The problem is this 3, right? Because it's bigger than the index, which is 2 in this case, right? Because it's not written, it's understood to be 2. So, you know, I could rewrite 2 cubed as 2 squared times 1, right? So this would be equal to the square root of 2 squared times 2 times 3, right? Whoops, and I meant not 2 squared times 1, but I meant 2 squared, or 2 to the first power, right? Which is the same thing as 2 squared times 2, right? So then, you know, I could split this apart. This would be the same thing as the square root of 2 squared times the square root of 2 times the square root of 3. Well, this first part, you know, just becomes 2, and this part I can write as a product, right? So this would be the square root of 2 times 3, which 2 times 3 is 6, right? So this is a simplified version of square root of 24, 2 radical 6, right? So what you're trying to do is pull out all those perfect square factors, right, and bring them out in front, right? So then the next one is 5 radical 18, right? So, you know, notice I have a factor times a radical, but that doesn't necessarily mean that it's simplified, right? And I know it's not, right, because 18 is equal to 2 times 9, where 9 is a perfect square, right, because that's 3 times 3, 3 squared. So in other words, 18 is equal to 3 squared times 2, right? And you could do the factor tree if you wanted for that. All right, so 5 times radical 18 is equal to 5 times the square root of, and I'll just rewrite this as 2 times 3 squared, right? Just rewrite 18. So then I can use the multiplication property that we looked at. This is 5 times the square root of 2 times the square root of 3 squared, right? And then this last square root I can simplify. The square root of 3 squared is just 3, so this would be equal to 5 times 3 times the square root of 2, which this is equal to 15 square root of 2. Right, so that's simplified. Right, so an example 5 is a little more involved here. We're trying to simplify the 4th root of 32, a to the 10th, b to the 19th. Right, so my index is 4. Right, so immediately, you know, I'm thinking of making some notes here. When I'm thinking about this 32, I'm trying to think, you know, what is this equal to in, you know, if in, as prime factors, right? So this turns out to be 2 to the 5th, right? So if you know, break this down off to the side, 32, right? That, you know, that's 16 times 2. 16 is 4 and 4, and each of these 4s can be written as 2 times 2. Right, so you can see there's 5 factors of 2, right? So that's where I get that from. And then this guy, I'm trying to, again, what I'm trying to think of is I'm focusing in on that exponent of 10. What's the biggest multiple of 4 that's less than 10, right? Well, that's 8, right? So I'm thinking a to the 10th is equal to a to the 8th times a squared. And then now I'm focusing on the 19 for b to the 19th. So again, I'm thinking of what's the biggest multiple of 4 that's less than 19. And that is 16, right? So b to the 19th equals b to the 16th times b to the 3rd power, b cubed. Right, so these are just kind of my initial thoughts. So the 4th root of 32, a to the 10th, b to the 19th is equal to, I could split these apart to be the 4th root of 32 times the 4th root of a to the 10th times the 4th root of b to the 19th. And then now I can apply kind of my thought process here. So this 2 to the 5th guy, right, I would be thinking that 2 to the 5th is equal to 2 to the 4th times 2 to the 1st, right? In other words, 2 to the 4th times 1. So 4 is the biggest multiple of 4 that's less than 5, right? So you're kind of applying the same thing like with the variables, right? So rewriting this, I would have the 4th root of 2 to the 4th times 1, 2 to the 1st, sorry, times 2. Oops, I wrote that up here too, sorry about that. This would just be times 2. Guess my mind is focusing on that exponent of 1. Right? So then this would be equal to the 4th root of, and then a to the 10th, I could rewrite that as a to the 8th times a squared. Oops, and there's a times in between, jeez. And then I would have times the 4th root of, so I'm going to rewrite b to the 19th, so that would be b to the 16th times b cubed. Right, so just applying my thought process there. So then this would be equal to, so now what I can do is I can split each of these up, right, using that multiplication property of radicals. So this would be the 4th root of 2 to the 4th times the 4th root of 2 times the 4th root of a to the 8th times the 4th root of a squared times the 4th root of b to the 10th times the 4th root of b cubed. Right? So then let me write down these first two here. So a to the 8th, that's the same thing as a to this a squared raised to the 4th power. Right? So I'm going to rewrite it like that. This would be times the 4th root of a squared times the 4th root of, that's a 16. I didn't make that real clear here. B to the 16th. Right? So this would be b to the 4th power, all raised to the 4th power, right? Because 4 times 4 is 16. And then times the 4th root of b cubed. And then so now what I'm thinking is I can simplify this one and this one and this one. Right? So the 4th root of 2 to the 4th is just 2. And then the 4th root of 2 I can't do anything with, so I just leave that. And then here, a squared to the 4th, and take the 4th root of that, that's just a squared. And then this one doesn't simplify, right? So I'll just write that down, the 4th root of a squared. And then the next one, b to the 4th raised to the 4th, and the 4th root of that, right? These 4's are cancel out, right? So that'd be times b to the 4th, and then times the 4th root of b cubed. Right, so just looking at each of those individually. And then now what we could do is rearrange some things, right? So I have kind of these guys that aren't underneath a root, right? So we got 2a squared times b to the 4th. And then the ones that are left, notice they all have the same index of 4. So I can apply the multiplication property of radicals and put them all, multiply them all under the same radical. So that would give me 2 times a squared times b cubed. Right? So that's a simplified version of that. 2a squared b to the 4th times the 4th root of 2a squared times b cubed. Right? So then concept 3, we want to simplify radicals by using order of operations. Right? So in part A, the first thing we'd want to do before applying the square root would be to divide. Right? So here, right, we want to use the exponent rule when I divide, which I'll subtract their exponents, right? So this would be the same thing as the square root of v to the 21st minus 5, right? So this would be the square root of, and then this would be what, v to the 16th power. And then I can rewrite 16 as v to the 8th all squared, right? And that would be the square root of all of that, right? Because 8 times 2 is 16. What I'm thinking. So then the square root is going to cancel out with the 2, so I'm left with just v to the 8th power. Right? So then in part B, and I got the fifth root of 64 divided by 2. So 64 divided by 2 is 32. And as we looked at before, 2 to the fifth equals 32, right? So this would equal the fifth root of 2 to the fifth power. So the fifth root in this exponent of 5, those are going to cancel each other out. So we're just left with 2, right? So in example 7, we have 2 times the square root of 300 divided by 30. And immediately my mind is focusing on the 300 since it's under the square root, right? So first thing I would want to do is try to come up with the prime factorization. So 300 is 30 times 10, right? And 30 is 5 times 6, so 5 is prime. And then 6 I can break down as 2 times 3, so both of those are prime. And then 10 I can break down as 2 times 5, right? So 300, the prime factorization of 300 is equal to 2 squared times 3 times 5 squared, right? So then this would be equal to, so just substituting that in for 300, 2 times the square root of 2 squared times 3 times 5 squared all over 30, right? So this would be equal to, so applying the multiplication property of radicals, this would be 2 times the square root of 2 squared times the square root of 3 times the square root of 5 squared all over 30, right? Well, the square root of 2 squared is just 2. So we'd have 2 times 2 times square root of 3 times, and then the square root of 5 squared is just 5, right? They cancel each other out, the squaring and the square root. So this is all over 30. So then what I would do is just rewrite, change the order of the 5 and the square root of 3. And then on the bottom, right, 30, we can see the prime factorization is here, right, this part of the 300. So this would be 2 times 3 times 5, right? 2 times 3 times 5 is equal to 30. 30 equals 2 times 3 times 5. Right, that's the prime factorization of 30. So then now we can just cancel out like factors since everything's multiplied in the top and bottom. So then what we're left with is 2 times radical 3 all over 3, right? So that would be the simplified version, right? And notice each of my simplified expressions meet those 3 conditions that we talked about, right? All right, so as usual, just let me know if you have any questions.